students. All right, ladies and gentlemen, today we are going to be doing something rather interesting, I think. We're going to be measuring the size of the sun. More specifically, we're going to be measuring the diameter of the sun. And some of you might be thinking, well, how in the world are we going to do that? Are we going to go on a magic school bus ride to the sun with a ginormous measuring tape? No, we're not going to do that. We're going to do it from the safety of planet Earth. Because just using a few basic materials and our noggin, we can use geometry and mathematics and what we already know to measure the diameter of the sun from here. That's right. That's right, ladies and gentlemen. We are going to determine how big is the sun. Again, more specifically, the diameter of the sun. And to do that, here's all we need. In addition to our brains, we're going to be using a meter stick. We're going to be using an index card with a piece of aluminum foil on it with a tiny little hole poked in the middle of the aluminum foil. I'll explain that in a moment. And another index card with some lines on it. Well, how in the world are we going to be using these things in order to measure the diameter of the sun? Well, check this out. If we refer to our diagram here, here is the beautiful sunshine. This is the meter stick illustrated here. And on one end of the meter stick, we're going to have the index card with the aluminum foil on it. And this tiny little pinhole actually acts like a lens. So that tiny little hole in the foil serves as a lens in order to focus the light. It's a pinhole. 150 years ago, there used to be such things called pinhole cameras. And it was simply a pinhole acted the same way as a lens to focus an image. And we're going to be focusing an image from that pinhole. On the other side of the meter stick is another index card, and that index card has a hole in the bottom, which actually is intended to slide back and forth on the meter stick. And you're going to be sliding it back and forth on the meter stick until the image from that pinhole is projecting a focused image of the sun on that card of a certain dimension. So this is the only thing you're going to be doing in order to measure the diameter of the sun. How cool is that? So let me explain to you the process here, and then we'll get into the math. So imagine on a sunny day, and hopefully today is a sunny day so we can do this outside. We are going to go out on a sunny day, and we're going to hold the meter stick over our shoulder. So we're going to hold it on our shoulder like this. And if you look at the way I am positioned, the sun will be toward my back. You want to face in the opposite direction of the sun. So with the meter stick resting on your shoulder, you're going to be facing the opposite direction of the sun. So the sun will be shining through the card taped at the end of your meter stick with a little pinhole in it, and that pinhole will be projecting an image on the other card, which will be the card you are looking at. So I'm going to be looking at the card, and you're going to be able to slide this card back and forth until you are able to project the image from the sun on the card, move the card back and forth until the size of the image fits within the lines. Now, let's look at this from another angle. Here's what's happening. You may recall the parallax method and what shape the parallax method utilizes in order to measure the distances to stars far, far away. We're using that same principle, the parallax method in triangles and similar triangles, to measure the diameter of the sun. How? Well, let's look at this diagram. Here we have the sun, far, far away. How far away? Well, the distance that is equal to the altitude of this triangle, which is line B. So we know how far away we are from the sun, and we're going to know that information. We're going to know side B. We're going to try and figure out the length of the length of this triangle labeled line A. That's what we're going to be looking for. And the way we're going to do that is, if you think about the rays of light traveling in straight lines, we're going to have that little pinhole here at the end of our meter stick. This is going to be the measured distance on the meter stick. And line C here is going to be the dimensions of the sun's image on that index card. So essentially what we're doing is this. We're using the principle of similar triangles to come up with an equation. And that equation, just like we used before, is the base of a triangle divided by the height of that triangle. In other words, A divided by B, as indicated here, is equal to the base of a similar triangle divided by the height of that triangle, which is C over D. So knowing this mathematical relationship between similar triangles, the really, really ginormous triangle made up of the distance to the sun and the diameter of the sun is simply equal to the similar triangle here on Earth, on our shoulder, the size of the image and the distance to the image of the sun. To put that in terms of words, here's what we've got. A is equal to the diameter of the sun. Here's A. B is the distance to the sun. Here's line B. C is the diameter of the sun image on our index card, right here. And D is the distance to the sun image from the little pinhole at this point here. Now, notice I've written the equation again, but I've written it a little bit differently, but it means the same thing. A divided by B equals C divided by D. So this is the information, these are the numbers that we're going to be collecting in order to solve for A. Now, some of those things we know, and some of them we're going to find out. For instance, the value for line A, we're going to call it X meters, and we're going to put all of our units in meters here to keep them all the same for the time being. A, X meters, that's what we're looking for. How big is the sun? What is the diameter? We don't know it yet, but you're going to know it by the end of the period. So we're just going to call that X for the unknown. B, the distance to the sun. We know that the sun is 150 million kilometers from the Earth to the sun. Now, we're going to express that in meters. And if you think back to the metric system, we know that there are 1,000 meters in a kilometer. So we simply add 3 zeros to our kilometers here. And so we've got 150 billion meters. That's how many meters it is from the Earth to the sun. 150 billion meters. All right. C. We have lines drawn on the index card that you're going to be sliding back and forth on your meter stick. And the lines in the middle are 1 millimeter apart from one another. You're going to be focusing the image of the sun so that it appears to have a diameter of 1 millimeter. 1 millimeter is the same as 0.001 meters, because as you remember, a millimeter is 1,000th of a meter. That leaves us only with one letter, letter D, the height of this triangle, and that is going to be the measured distance from the pinhole to the image when we get the image to be 1 millimeter in diameter. So all you need to do is this. You are going to be outside measuring the diameter of the sun by allowing the light of the sun to enter the pinhole, projecting an image that is 1 millimeter in diameter, and then measuring this distance on your meter stick. Once you've got that distance, you'll then enter it into this equation. So I've set it up for you here so that you can refer to it. It is going to be x, which is the value of A, we don't know what it is, divided by the value of B, which is 150 billion, is equal to the value of C, which is 0.001 meters, divided by whatever the measurement is that you have gotten from your meter stick. And then simply by cross multiplying, our end result will be this. X, which will be our answer, the diameter of the sun, will be equal to 150 million divided by your measurement in meters. So if all of this math and all these numbers have confused you, you can just pick it up at this last step. You're going to find your measurement in meters. So it'll be less than 1 meter. So it's going to be a decimal. Keep that in mind. You're going to take 150 million divided by your measurement, and that will be your answer for the diameter of the sun. Now, when everyone has completed the activity, I'll let you know what the actual diameter of the sun is, and we'll see which group was able to measure it most accurately. And I'll give you a bonus point if you and your teammate got closer than anyone else. So that is our lab activity for today. Now, I want to give an alternate just in case it's a cloudy day. We will be using something else in the classroom. In fact, we will be using an overhead projector. The overhead projector has a lamp lens of a certain diameter, which we will measure in the lab after we've calculated it to see who got the closest. But the process is exactly the same as what I described before. Instead of the distance to the sun being 150 million kilometers, in our laboratory, we're going to be 10 meters from the lamp, which translates to 1,000 centimeters. And the size of our image won't be a millimeter, it'll be a centimeter. Or I'm sorry, it will be a millimeter, which is 0.1 centimeter. We'll cross multiply exactly the same way in order to determine the value of X, which is the diameter of the lamp in the room. So if it's a cloudy day, we'll be doing this indoors, and we'll be able to measure the diameter of the light lens. So we'll again determine who is able to calculate that most accurately. So now we've got time to do either one or the other of the activities. So let's get busy. And for now, I'll say good luck and bye-bye.